Guys, welcome back to Acids and Bases. And in this section, I told you that we were going to move on to another topic, and that really involved structure. We are seeing this structure word pop up many times throughout our early lectures, and it's never going to go away. We're always looking at shapes of molecules and the way that these things order themselves in a 3D environment. We're looking at bond angles, we're looking at bond lengths, because all of this really plays a role in the organic chemistry and characteristic of that particular type of compound. So that's what we're going to focus on now. We're going to look at these structures, these components that we need to discuss, and we're going to relate how organic chemistry plays a role in acid and base chemistry. So what do I mean when I talk about structure? Well, we're talking about four different things here, and they're listed on the screen. The first one is En, which is electronegativity value. The next one is hybridization. Yes, if I go back and we talk about hybridization in the first lecture, remember, I told you build-up process, I told you foundation. If you go back and take a look at sp3 and sp2 and sp, it plays a role in acid-base chemistry. So we need to bring that back. We also need to take a look at size. You know, this is something that we've discussed in lecture 1 in that very first module. So atoms have sizes, atomic radii, all of this plays a role in acid-base. And then finally, substituents. And substituent is a fancy word that just means these things are attached to a molecule. These things are attached to a compound. That's what these things are all about. So those are the four components of the structure that we are going to focus on first in this section. And we're going to talk about how these relate to the acid and base world. Okay, so the first one we're going to talk about is electronegativity value. So if you go back to that first lecture module, you're going to see that we had a periodic chart of electronegativity values, and that chart had fluorine up here in the very corner, and we said that fluorine was the most electronegative on the chart. From fluorine, as we go down, the electronegativity decreases. And from fluorine, as we go across, the electronegativity decreases there as well. So what that means is that fluorine is the most electronegative, and as we go away from fluorine in either direction, either left-handed or down, that electronegativity decreases. Keep in mind that electronegativity, as a review, means electron greedy. So how greedy are you with the electrons? How bad do you really want them? And fluorine has the highest electronegativity, so that means that fluorine is the most greedy out of the bunch. So, in this first example, what we see is a couple of atoms that they've pulled from the table, and they've ranked fluorine here, and they've labeled it as the most electronegative. And as we go away from fluorine, this electronegativity goes down and down and down, folks. Okay? So this is the first relationship that they want you to go back and remember. They want you to say, knock, knock, knock. Remember, we talked about this in the last module, in the last chapter. It's coming back. So what does this really have to do with acids and bases? Well, here's how it relates. In the second line item, you see the same atoms that are listed: F, O, N, and C, just like they listed up above. Well, if we add on other things to those atoms, and in this case what they've added on were hydrogens, enough hydrogens to give it a formal charge of 0, enough to get it happy. We don't want to play around with charges right now. But if I take a look at the bond between H and F, the first line basically says that F is the most electronegative. F is the most electron greedy. That means the electrons that are in this bond, if H and F begin to play a tug of war here between these electrons, that the glue that holds these two atoms together, F is going to win. Fluorine will win every single time. It's the most electronegative. It is the strongest. It is the most electron greedy. So all of these electrons are going to be surrounding fluorine because of that, for the most part. And this leaves poor little old hydrogen exposed. Electrons do come around. He gets to play with them a little bit, but not much. Fluorine really hogs up all of the toys. And hydrogen just kind of has to wait. Again, you always feel sorry for hydrogen in these cases. He just gets knocked around whenever he can. Poor thing. So if fluorine gets all of the electrons, and if fluorine is the most electron greedy, then that means that this side, which is the hydrogen, becomes more exposed. This side feels left out. And if fluorine sucks all of the electrons away, pop, hydrogen is easily kicked off. Because he's not going to hang around. He's not going to feel wanted. There's nothing here holding him down into a relationship. So H and F get a divorce at this time. H and F, hydrogen looks at this relationship and says, you know what? You get everything out of the relationship. I mean, I don't really get to make any decisions at all. Here you are coming in every day and you are hoarding up the checking account, you're hoarding up the debit cards, you're hoarding up the clothes, you're hoarding up the food, you're hoarding up everything. There's nothing here for me. And hydrogen decides to split. And you know what? Fluorine doesn't actually care. It's electron greedy. That's all that it wants. As long as it gets those electrons, fluorine is going to be happy. And because it's electron greedy, because it has a high electronegativity value, then that also means that when hydrogen does split, the fluorine is also the most stable. I mean, that's what it wanted in the first place, wasn't it? You know, I mean, again, a bad relationship is happening here. Fluorine is just siphoning everything on its side. And then if it does divorce from the hydrogen and hydrogen gets kicked to the curb, fluorine's not going to care. Fluorine, that's what it wanted in the first place. So fluorine is perfectly okay on its own because it is electron greedy and now it has the electrons. Well, if we move on to the oxygen, the same description can happen here, right? Oxygen is electron greedy. It does have electronegativity value to it, right? It's one of the higher ones on the chart, but it's much less greedy than fluorine is. Well, if something like an oxygen-containing molecule forms, oxygen is electron greedy. Oxygen will soften the electrons up around it, but not the extreme that fluorine would do. But it does. And hydrogen can feel left out, and that hydrogen can leave as well. And when it does, oxygen's just like, well, whatever. I mean, I guess I hope that you would hang around, but you know what? Give me a week, I'll get over it. And that is why OH is also very stable. But it's not as stable as fluorine because, you know, there's a little piece of oxygen there that does miss that hydrogen. It wasn't super electronegative. It was much less than fluorine was. But you know what? It can take care of itself. It just needs some time to get over that breakage or that divorce between the H and the O. Again, same narrative. If we take a look at nitrogen, nitrogen is even less electronegative. So nitrogen can form a bond, and you know, nitrogen does like electrons. It does soften them toward it because there is electronegativity assigned to it. It's close to fluorine, but it's nothing like fluorine behaves. And it's actually nothing like oxygen behaves either because it has much less electronegativity. So in this case, nitrogen is a little bit more dependent. It is in a relationship. It does like to spend on itself. It does like to think of itself more so than others, but not as bad as O and F. So nitrogen is in this relationship, and nitrogen's electron greedy, and nitrogen is sucking some of the electrons its way, but it's a little bit fairer to hydrogen. Well, just because it's a little bit fairer doesn't mean that it is exactly fair. And we can get a split of that hydrogen in that relationship as well to create an NH2. So it is a stronger acid than some of the others, but nothing like oxygen or fluorine. And again, because of that, it's a little bit less stable, but it's on the stability side, just not as stable as F or O. And then finally, CH4. If I take a look at CH4, this is the lower acid of the bunch. If you look at the electronegativity values between carbon and hydrogen, you're looking at like 2.5 and 2.1. So if carbon is in a relationship with 4 hydrogens, I know that's kind of a weird relationship, isn't it? Well, because the electronegativities are pretty close, this is a relationship that is pretty equal. You know, carbon does like electrons, hydrogen does like electrons, and in this case, carbon and hydrogen maybe share the bank account evenly. So carbon gets them sometimes, hydrogen gets them sometimes, neither one of them feel left out. This is a perfectly good relationship here. So because of that, there is no need for this carbon and hydrogen to split. I mean, there's no urgency here. This carbon is not electron greedy like fluorine is. It's not a one-sided relationship. So if it's going to keep those hydrogens because everything is shared equally, then this thing is not going to be classified as an acid, right? And that's why it's one of the lower ranked acids of those 4, because there's no need for hydrogen to be donated. That is what this is all about. Well, if there's no need for hydrogen to be donated and we form a CH3 minus compound, this thing is going to be very unstable. And the reason is because carbon really didn't want hydrogen to leave. Everything was good. I mean, it seemed like everything was going to plan here. And then if hydrogen does get removed, that carbon's going to look at that bond and say, wait a minute, you know, I didn't want you to go, so why did you leave me? And carbon gets very disturbed because of that. If a CH3 minus is formed, carbon goes through emotions. Carbon goes through a period, a very long period of saying, this is not working for me. I need something here in place that is a bond between another atom. And it will constantly reach out and search for whatever that is that could help satisfy that need. It always has to be in a relationship. That's what it boils down to. So because of that, the stability of a CH3 minus is very, very low. Folks, all of this is based on electronegativity. This electronegativity we talked about on the very first lecture module, and it's coming back to us now, and it's playing a role in acid and base, and it will always play a role in organic chemistry. So therefore, electronegativity we have to get used to, and whenever we can bring it into the discussion, we're going to do that. That way it will always stay fresh and active in your mind, okay? Here's another one. Why are alcohols stronger than amines? Well, this kind of goes back to electronegativity again. You know, we looked at pKa values, pKa of 15.5 and pKa of 40. So what we're saying here is that this alcohol group, this is more acidic. And acidic means that it donates a proton. So that means that this proton, poop, off it goes. Alcohols do this much easier than amines do. Well, why is that? You know, a couple of videos back, we just kind of threw out these pKa numbers and we said, hey, you got to keep in mind, alcohols are 15s, amines are 40s, carboxylic acids are 5s. But I never really kind of compared them further than that. But now we can make an argument of why this is the case. And part of that reason, part of that answer is electronegativity. We already know that oxygen has greater electronegativity value than nitrogen does. That means oxygen, that is more electron greedy The bond between the OH, that's electrons. This oxygen's going to suck those electrons around it. That leaves hydrogen exposed and left out, and this hydrogen is more than willing to skip. And that bond breaks. And now we have just defined an acid. That is one of the reasons that proton does decide to leave that molecule. It's getting nothing out of the relationship. So because of the pKa 15.5, that means electronegativity difference of O and H. Oxygen is the electron sucker. That hydrogen is going to be spit off. But, this is not the worst one. There's other things that we can compare. This is just the one that's on the screen, and it relates to alcohols and acidity, so we talk about it right now. We'll worry about the other ones much later. Well, compare that to the amine. The amine is a nitrogen-based compound, right? I mean, everything else is pretty much the same, except the N and the O. So nitrogen is less electronegative. It's less electron greedy. The electrons in those bonds, well, it wants them, but it's not going to treat it like oxygen does. So this hydrogen can be removed, and it could be removed, but it's not going to be as dramatic because the electronegativity is lower. And that is why the pKa, it's not as acidic. It's a higher pKa value. It's not as acidic because there's no immediate need for hydrogen to be removed right now at this time. This relationship is a little bit better than the rocky relationship that the O and the H have. And fluorine is even worse. Folks, I'll go ahead and tell you that fluorine-based organics are very explosive. Okay? You talk about a bad, unhealthy relationship. Fluorine-based compounds, they are calling the cops all the time to take care of problems that are happening. Okay, you get me? Fluorine is a very explosive organic, and we stay away from them whenever we can. We're actually going to get to a point where we will not even talk about fluorine any longer as a halogen. We'll talk about chlorine, bromine, iodine, but we're going to leave off fluorine for the most part throughout the semester because these compounds are so explosive, they are so dangerous that we just don't even want to fool with them. We don't even want to carry them in our lab because they're that dangerous. That is why fluorine is such an electron-greedy atom that whatever you put it in the world of organic, it is going to start ripping those electrons away to satisfy its own need, and it could care less about anything else around it. You probably know people like that. Next time you see that person or those people, think about fluorine. They're walking fluorines that are out there in the public. You know what I mean by that too, right? Well, that's not the only thing that we can compare. We can also compare protonated compounds, right? We said that we can protonate compounds. This adds an extra hydrogen, and we get these positive charges that come along with it. And this dramatically shifts the pKa's much, much lower. They are positive driven at this point. They would love to get rid of those hydrogens, or at least one of them, to become neutral at this point. So all of these pKa's dramatically plunge, and that's what we're seeing here. The alcohol before, that was around a 15. Now we're around a -2. And then the amine before was around a 40, and now this protonated amine, that's now a 10. So all of these dramatically shift, but folks, the order of this is no different. Okay, the explanation of why this is lower than this, which means that this is more acidic, all again deals with electronegativity. Oxygen is still more electronegative. Therefore, oxygen is still more electron greedy. If oxygen's more electron greedy, it's going to suck the electrons from that bond more, leaving hydrogen out in the cold, and now hydrogen, pop, off it goes. Therefore, it meets the definition of an acid much easier. This is why acids behave the way that they do. One of the reasons, especially if you have different atoms like this, and different functional groups like we've talked about, is all due to the electronegativity of the atom. So, like I've said before, En values are very important. And I'm going to be honest with you. You probably talked about electronegativity in a general chemistry course. I hope that you did, if it was a proper general chemistry class. But even with me, we talk about electronegativity, we briefly discuss it, we do not go into detail because there's other things that we have to talk about in that mix. Folks, electronegativity is one of the most important things in organic, and you're starting to see it now. We saw it in the first lecture module, we're seeing it in this lecture module, and we're going to continue to see it over and over throughout the entire semester. It is one of the major driving forces that makes all of this happen, and we only give it maybe a few minutes worth of importance in general chemistry. But organic completely centers around it. So, if we talk about electronegativity, we can also talk about electronegativity in terms of other things. Okay, if I go back to this example, O's and N's and F's, well, we can compare them that way, but we can also compare electronegativities in other ways as well. And that's what we're going to learn about in the next lecture video. So come back, don't take a pause, okay? If you've got to go take a potty break, go take a potty break. But come back, and then we'll continue electronegativity discussions because we're on a roll. So watch the next video pretty close to this one. We'll keep trucking on, and we'll talk more about electronegativity and how it behaves and affects acid-base chemistry.